Okay, so guess I'll have to make the next test a little longer. Getting really soft. Okay. So we started at the end of class on Thursday talking about the relationship between SN1 and E1 and what E1 involves. So let's go back to that reaction. So right now what I'm going to do is I'm going to tell you that you need to do an E1 mechanism. And you can only do an E1 mechanism on a secondary or a tertiary alkyl halide because the first step is going to be the same as an SN1 reaction. And the more important thing is that an E1, that the idea of the one mechanism is it involves a carbocation intermediate, and a two mechanism does not. So anytime we're going to broaden our reactions out here in the next few days, then we're going to broaden the reactions out, and it's always the key thing is 2 no carbocation, 1 carbocation intermediate. So this is the reaction that we did the other day with E1. So let's write the complete mechanism for this. And the first step is going to be break the carbon-chlorine bond, so that I'm going to go through a transition state that looks exactly like the transition state for the first step in SN1 because they share the same step. So the carbon's going to be slightly positive, the chlorine's going to be slightly negative because I'm going to end up with a carbocation and my Cl minus. So that's going to be the first mechanism, the first step in the mechanism for either SN1 or E1. And that's why we're going to modify our chart here today and say, okay, wherever we had SN1 on our chart, we're going to want to put E1 as well. Because whenever you do SN1, you're always going to get a little bit of E1. And the issue is going to be, when do we get purely E1? And the answer is probably going to be only when I put E1 over the arrow. In reality, we're probably going to get a mixture of SN1 and E1 all the time. Okay, so that's the first step in the mechanism. Now we've got our carbocation. So now that carbocation, the carbon with the alkyl halide, with the halide attached to it, was called what kind of carbon from last week? It had a Greek letter. That's the alpha carbon. And so what I got to do now is I've got to look for my beta carbons because I'm going to lose a beta hydrogen in the next step. So the alpha carbon is always the carbon with the leaving group, which is the carbon that becomes the carbocation. So let's work with the beta carbon that's on the left here. So I'm going to write that with an H. Instead of writing it as a CH3, I'm going to write it as a CH2 with the H on it because now I'm going to show the loss of that beta hydrogen. So in the mechanism, what's going to happen is that hydrogen is going to be lost as an H+, and its pair of electrons is going to go to form the carbon-carbon double bond. Okay. What's the transition state going to look like for that? Well, let's go down to the final product. So there's my final product plus the H+. So it's going to be that alkene, 1-butene in this case. And again, if you have to do that in order to write the transition states, that's perfectly fine, because the transition state is going to be the average. So now I'm going to write my structure with the single bonds intact and with the atoms intact. So in terms of the average then, I'm averaging charges, and I'm also showing the bonds that are being broken or made. So in this case, where should the dotted lines go? What bond is being broken and what bond is being made in this case? The H that's being lost is an H plus. That carbon-hydrogen bond is being broken, and so we should put a dotted line there. And then what bond's being formed? And so there should go, their dotted line should be there to form the forming double bond. Okay. So I don't know, I find it easier to think about what bonds are being broken and what bonds are being made, and that tells me where the dotted lines should go. Then in terms of the charges, you could use the average between the reactant and the product to give you the delta plus charges in this case. So who needs to get a delta plus charge?
Top hydrogen.
And
Carbon.
there was the carbocation. Okay, so there's our transition state for forming a product, for forming an alkene product. So again, dotted lines, bonds that are being formed or broken, charges. What I'm doing is I'm losing an H plus, so really the plus charge is being transferred from the carbocation up to the H plus. And remember, charges don't really transfer, electrons do. So as the plus charge moves to the carbocation, that means the electrons are moving in the opposite direction. Okay. So there's the first, so there's the mechanism for that. So there is another beta carbon. This is alpha, there's a second beta carbon. So I want you to write the transition state and the final product of now losing that beta carbon on the right-hand side. So you're going to do the same thing I just did, which is that pair of electrons from the CH bond is going to go to form the double bond, and then you're going to lose now the beta hydrogen on the right. And then you're going to write the transition state and the second alkene. You got to show the arrow of the pair of electrons moving from the right-hand hydrogen down to form the double bond. So toward the positive form a double bond there. Because otherwise you're going to end up with a carbon with 5 bonds. So that's going to go there towards, remember the arrows always move towards the positive charge. And in the end, you can't end up with a carbon with more than 4 bonds. Another test for your delta positive charges are that delta positive charges will go on atoms that had a positive charge. So if an atom doesn't have a positive charge, it's not going to be, it's not going to have a delta positive charge in the transition state. So if that's at that one, it's not positive, right? You've got to move your positive charge over. What you're showing there is that the electrons are the positive charge. And it's only All right, so how's it, so most of you got this, but let's just, so the arrow should go from this pair of electrons to, bless you, form the double bond like that, okay? If your arrow isn't quite looking like that, you want to make sure it looks like that, because it's not going to the positive charge, it's going to form the double bond. And then your transition state would have a partial double bond to that carbon, the partial bond to the hydrogen breaking, a delta positive on the hydrogen and delta positive on that carbon that was the carbocation. And then the final product would have now the double bond in the middle of the butene. We're in the middle of the butane chain. So that molecule is 2-butene. So we're going to get some practice on that this week. Yeah. Yes. Yeah, there's only one arrow, and that is the pair of electrons moving from the hydrogen to the CH bond to the now carbon-carbon double bond. You always lose the beta. You always lose the beta hydrogen in this mechanism. You can't lose an alpha hydrogen. You can't lose a gamma hydrogen, because the whole idea of this movement of this electron pair is simply that you're forming the double bond. So the carbon plus is getting its eight electrons back in terms of sharing, and then the H plus, the carbon that's losing the H plus isn't losing or gaining anything, but the hydrogen is losing its pair of electrons. So those are going to be the steps for an E1 mechanism. Form the carbocation, lose a beta hydrogen. Okay. And like I said, we're going to get some practice on that both inside and outside of class, because this week I will give you a take-home quiz problem. And it won't be today, but it's got to be tomorrow so that you can give it to me on Wednesday, because the 4th is no class. So that's how we write the mechanism of E1. The problem is, as we talked about last Thursday, is that if I'm going to do an E1 mechanism, in this case, I'm going to get two possible products. Now, just like you had to do today, in terms of writing the mechanism, but then also writing the products, you're always going to have to do that. you're always going to have to write the mechanism, you're always going to have to write the products, and so you're not necessarily going to have time always to write the mechanism. And you'll have to write the products. So in this case, I can write the products of any reaction without going through the mechanism, simply by saying, there's my alpha carbon, there's my first beta carbon, there's my second beta carbon. As long as the beta carbon has a beta hydrogen to lose, you're going to get that double bond between the alpha and the beta carbon. So we're going to lose basically an H, we're going to lose an H and the Cl. So if I'm writing those products, I would say, okay, if I lose the left-handed beta hydrogen, I'm going to get 1 butene. If I lose the right-hand beta hydrogen, I'm going to get 2 butene. So those are my two possible products. And notice again that what I did was I lost the beta hydrogen, I lost the leaving group halogen, and I formed a double bond between the alpha and the beta carbons. So to write these products, you don't need to know anything about the mechanism, but you still do. So when we get two products, then our next question is, what's the major product? And so that led us to Zaitsev's rule. And so in this case, whenever we do an E1, the major product is always going to be the most substituted product, which is also the most stable product. Okay. So E1s will always give us the most substituted, most stable product. That will always be the case. Now, why is the most substituted product the most stable? If you have a carbon-carbon double bond, you always have 4 things attached to it. Go back and remember EZ, right? We always had 4 things. That's how we were determining EZ or cis-trans. Now, a double bond itself is an electron withdrawing group. It likes electron density. So the more electron density you can push into that double bond, the more stable that double bond will be. And what kinds of groups push electron density? Well, we saw that when we looked at carbocations. What type of carbocation is the most stable? Tertiary. Why? Because it's got 3 alkyl groups on it. What are those 3 alkyl groups doing? Pushing electron density into the plus charge, getting it closer to 8. Have 8 valence electrons. So same thing happens here. So when you put a carbon group on the alkyl group, remember the hydrogens are delta plus at the expense of the carbon becoming delta minus. That delta minus carbon can now push the electron density into the double bond and make it more stable. So the more stable double bond is always going to be the one with the most alkyl groups. Now you might say, well, what if you had, 1 alkyl group on each side? You can probably imagine that if you had 2 alkyl groups, it would be better to have them trans than it would cis because of steric interactions. So in this case, trans is going to be more stable than cis. So trans is going to be more stable than cis. But the first way to look at stability is how many groups are attached to that double bond. And again, you can have a maximum of 4. And anything that's not an alkyl group is going to be a hydrogen. So you can also count hydrogens and say, oh, that double bond has 2 hydrogens, therefore 4 minus 2, it has 2 alkyl groups. If it has 1 hydrogen, it has 3 alkyl groups. So the more stable, the more substituted, I'm going to use those synonymously for double bonds. The more substituted is the more stable. And what Zaitsev's rule said is that when you do our interpretation of Zaitsev's rule is when you do an E1 mechanism, any elimination that goes through a carbocation intermediate will automatically give us the most stable product, therefore the most substituted. And if you're going, well, why are you making a big deal about this? I'm making a big deal about this because there's going to be other elimination reactions that give us the least stable, although it's not really going to be the least stable. Okay. All right. So those are our two big things here with E1. First of all, the mechanism has the same first step in terms of losing the carbon-chlorine bond to form the carbocation. Once I form the carbocation, I still have my beta hydrogens, and I can lose the beta hydrogens then to give me the alkene product by having the pair of electrons move from the CH bond to form the double bond, and then the transition state would have a partial double bond, breaking that carbon-hydrogen bond, and the charge being transferred from the H to the C, or vice versa, from the C to the H. Right, so we need to know the mechanism, and then we need to also be able to predict the major product of the reaction. Everybody kind of with me? So if I'm counting, that's two things for today. I will not stop if I get to 5 to 7. We'll continue on, but those are the 2 big things. The mechanism, how do I determine the major product? The major product is going to be the most substituted double bond. So, we're going to have to work rings in here. So what I would like you to do with this reaction is, number 1, I would like you to write the possible alkene products if this is E1. And then we're going to vote on a major product. So you've got to label your alpha carbon, which is the carbon with the leaving group. The beta carbons are next door. If the beta carbons have a hydrogen, you're going to lose the beta hydrogen and the halogen to form double bond. So the first thing you want to do is label the alpha and then the beta, any and all beta carbons that have hydrogen.
Then we get it.
So there's your two, so now, then so now there's a beta hydrogen and the chlorine. And so you're gonna lose that from each one of the beta hydrogens to give you the different products. It's now a question of which one of those is the beta product. Or the both of them. So what those two which ones are the So now you're going to choose which one of those is the major product. The major product is the one that is most substitute, which is the most stable. So number that with your system. This is good. Yeah. So then you're going to use the data. So then you go, choose one, and look at the product, choose the other one. Well, so then so that. So we want to count alkyl groups
once we get the double bond. So in this case, here's my alpha carbon, there's beta carbon 1, beta carbon 2. So do the beta carbons have hydrogens? Yes. So that means that if I lose the left-hand beta hydrogen and the Cl, I'm going to form the double bond to the ring. If I lose the right-hand beta hydrogen, I'm going to form the double bond in the middle of the chain. So if you want to call this A and B, if I lose HA, beta HA, I get A. If I lose beta HB, I get B. And so then the question is, which one of these two is the more stable product? And we can go ahead and vote with the cards. So if you wanted to, you could basically, if you think about this, I can draw the structure without the chlorine, and then I figure out where the double bond goes. Okay. questions. Okay. So A, B, and I guess C would be if they were the same. If you're going to get like a 50-50 mixture. Okay, and we have 7 A's and 4 B's. I'm a little puzzled by that. Because I could have sworn when I walked around there weren't 4 B's. Okay, how many alkyl groups are attached to double bond in A? Give me a number. 3. So again, if you don't know, draw in the hydrogens and subtract hydrogens from 4. So there's 3 alkyl groups attached to the double bond in A. How many in B? 2. So which one's more substituted? A. A's more stable. So we can do these kinds of problems. I can just move the chlorine around and see where we would end up. So for instance, I could move the chlorine to this position and say, okay, if I'm going to do E1, what I'm going to ask you to do next week is I'm going to say, write all the possible products and then circle the major one or tell me which one is major. Okay, so in this case, how many possible products are there? 3. Are any of them? So let's write all 3. So here's my alpha, then here's a beta carbon, here's a beta carbon, here's a beta carbon. So if I'm writing the products, let's call this one beta A, beta B, beta C. All 3 of those have hydrogens. If a beta carbon does not have a hydrogen, you can't form a double bond there. Because if you do, in the end, you'll see that that carbon gets 5 bonds, which is still not allowed. So product A would have the double bond like that. Right? Do we agree? It doesn't matter if it's inside or outside the ring. It's a double bond. So yes, whether the double bond is as I've drawn it there, outside the ring, or if I wrote the double bond inside the ring, it's still a double bond. No, when I first started doing that, that's a potential source of confusion. So it's a good thing you brought that up. All right, so there's A. Then what's B going to look like? That, and then what's C going to look like? That. So I'm forming the products by forming the double bond between each of the alpha and the beta carbons. So the question then becomes, which one of these is going to be the major product? This is one where I wish I had more choices. So I'll make one more choice, since you have a D. For D, let's say, we'll call it all or major. So for this reaction, which product is the major product? A, B, or C, or D, that they're all major? This is where if I had clickers, I could go A and B, A and C, B and C, A, B, and C. Okay. So which one is the major product? A, B, C, or all of them? All right, let's see what we've got. Oh, we've got 4 A's, 1 C, and 6 all are major. Okay, let's go through how many alkyl groups attached to each one of these products. For A, how many alkyl groups? 3? Do we agree that there's 3? For B? 3? For C? 3? So if they all 3 have 3 groups, 3 alkyl groups, then they would have the same energy, according to our rules, which is totally based on just simply the number of alkyl groups. Now you could say, is having the double bond inside or outside the ring more stable? There probably is inside or outside being more stable, but we're not gonna go into that level of detail. So we're just gonna say 3 alkyl groups, they have the same stability. If you don't see that, then my suggestion is let's put in the hydrogens. And you can see that each one of the double bonds has 1 hydrogen. So that means the rest of those groups are alkyl groups. Are these 3 products unique? Are all 3 of those different products? And what do I mean by different? I mean, do they have, are any of these structural isomers? Do all 3 of them have different IUPAC names? Are there any 2 that are the same? Okay, why do you feel that? And it's always better to think than feel, but that's just me.
I think they would do the same. I don't know, because they have a double bond on like the same, not like the same carbon that's attached to the alkyl group.
Okay. So what's attached to that double bond? In each one of those double bonds, the ring is, and then there's an ethyl group and a hydrogen. Right? Ring, ethyl, hydrogen, ring, ethyl, hydrogen. Do they have the same name? Well, the question would be, how do you name alkenes in rings? Automatically, carbon 1 would be the carbon. Well, carbons 1 and 2 have to be the double bond, and then you would choose number 1 being attached to the first alphabetized substituent. So in each case, those 2 are 1-ethyl cyclohexene. Would be the name of those. And if you don't like that, think about taking B and rotating it 180 degrees. And if you rotate it 180 degrees, the double bond would move up to the top and the ethyl group would stay where it's at. So A and B then are the same product. So part of the reason why all three are the major product is because A and B are the same. And then that product has the same number of alkyl groups as C. Right, is everybody okay with that? Okay, so SN1 and E1 are going to occur whenever there's SN1, there's always going to be E1. Why? Because if we go back to that first step of the mechanism, let's say we were writing the mechanism of that reaction we just did, we would break the carbon-chlorine bond, we would end up with a carbocation, and now it's a question of timing. Does the nucleophile come in and add to the carbocation before the beta hydrogens get lost? And so whenever you're doing a reaction, that's E1, you're always going to get a little bit of, whenever you do a reaction that's SN1, you're always going to get a little bit of E1 product. Simply because the nucleophile may not add fast enough, and there may be a few beta hydrogens that get lost along the way. So for instance, if I was to react this chloroethyl cyclohexane with something like water and say, what are the major products of this reaction? You would look at this and go, that's a tertiary plus a weak nucleophile, which makes the mechanism SN1, and now we would say that that's not only SN1, but it's also going to be E1, so that I'm going to get my substitution product, and I'm going to get my major. Usually what I say is write the major elimination product. And in this case, we know the major elimination products had the double bond inside and outside the ring. So these would be our major E1 products. What would our substitution product be for this? So I'm adding H2O to this alkyl halide. That's a substitution. What should go where? Well, first of all, it's substitution, right? So what do I put where the chlorine was? I'm going to put an OH group where the chlorine was. And so those three would be my major products of the reaction. Yeah. It's possible. I mean, it's possible if I raise the temperature that I might get more E1. Or if I use, see, this is what's difficult about this. Because we always get the SN1 when we get an SN1 reaction, does it matter how strong of a nucleophile I use? when you're doing SN1, does the strength of the nucleophile matter? No? So you could say, well, in order to make the E1 happen more, I'll just use a crappier nucleophile. But then it's a 1 mechanism, so the strength of the nucleophile doesn't matter. So we're going to treat E1 here as a side reaction. If I want to make the double bond, there's a better way to make the double bond. So E1 is going to kind of be our side reaction here. The only time I'm going to ask you to write the product as only E1 is, as I said, if I give you a reaction, I put E1 over the arrow, I want you to write the E1 product. But outside of that, in real life, I can't go to the lab and say, I want to do an E1 reaction. Really, I don't think I can. So it's not a good way to make a double bond, to make only a double bond. So we're going to treat the double bond as if it's a nuisance. So in a problem I'd give you, I'd say, write the major products of the first of all, identify the mechanism, so you still got to know the chart. And then after that, what would be the overall, well, let me go back. So if I give you this, you got to say, okay, this one's tertiary plus neutral, SN1, now SN1 plus E1. You would write the SN1 product plus the major E1 reaction. So if I asked you this as a mechanism, you would have the SN1 mechanism and you would have the E1 to form the major product. So you're going to have to write mechanisms again next week? Yes. Including SN1 again. Okay. So that's SN1. It's going to be with E1. Everything that's true about E1, or everything that's true about SN1, is true of E1. So all those characteristics are exactly the same. All right. So let's see, where do I want to go? Do I want to go to E2 or do I want to go to carbocation rearrangements? Against my better judgment, I'm going to go with carbocation rearrangements, because E2 is chapter 9 and I think we're still in chapter 8 if we do carbocation rearrangements. All right. So there are reactions that you can do that don't quite give you the products that you predicted. I will give you one example. And when I give you this example, I always go back to the idea that this is sort of a reaction that happened in lab when I taught 25 years ago at The Ohio University. Right. They need the in front of it as badly as everybody else does. So we were doing a reaction and something like this. And when we did this reaction, what would you predict the reaction to be? If I asked you for the mechanism of this reaction, what would you say? What? It didn't react. Why not? Okay, so it's a primary and a weak nucleophile, which means it shouldn't react. Okay. So maybe I go like this. I say, well, okay, I'm going to use hydroxide in this reaction. What would you predict? SN2, so what would be the final product? So have the same structure, except put an OH where the Cl is. So, do we agree that would be the major product? And I'm going to add something to this to say, well, you know what? I could get the water to react if I applied enough heat to the reaction. So if I apply enough heat, I can get this reaction to go. Or anyway, that's my assumption. So I say, this reaction shouldn't go. Let's try some heat. Let's see if it works. So the product that I got out of that reaction looked like this. I got that product. When I do it with hydroxide, I get a little bit of that product. I might get this as the major product, but then I get a little bit of that product. And so you're looking at that product going, where did that come from? Right? Now, I'll go back and I'll tell you the exact reaction that we did. But if I do this reaction either with some heat or at room temperature with the hydroxide, I'm going to get some of that as a product. And the question is, where did that come from? Well, that came from what's called a carbocation rearrangement. So let me show you the carbocation rearrangement that occurs in this case, and then we'll look at a couple more. Particularly with this molecule. Yeah.
What do you do this because it wants to become more stable with the carbocation rearrangement?
Yes. Carbocation rearrangements always occur to form a more stable carbocation. That's our guiding principle in this. You're only going to get well, there's two principles. You're only going to get a carbocation rearrangement when I tell you to do it. And then secondly, we're only going to get a carbocation rearrangement if you form a more stable carbocation. Cameron?
I thought there was no carbocation in the
There aren't, which means that if this is going to go by a carbocation, it's going to have to change mechanism and go by an SN2 or SN1. So here's what can happen with this molecule. What can happen with this molecule is that, let's say, I'm going to give this human characteristics. This primary alkyl halide can't react with water because water is a weak nucleophile and it could only react if it became a carbocation. This molecule right here says, you know what, if I had enough energy, I could become a carbocation. And you would say, no, because if you break the carbon-chlorine bond, you're going to form a primary carbocation, and there's not enough energy in solution to have that happen. And it says back, but I can do this. what if I slide my hydrogen over there, so that hydrogen moves with its pair of electrons over to the primary carbon, and then the chlorine gets kicked off. So this is what we would call a hydride shift. So that H minus, that H is going to move as an H minus. So if you give that molecule enough energy, it could do that. What's the transition state for that going to look like? Well, let's figure out what the final product's going to look like. So the final product is going to have this CH2 with that H on it, and then the Cl minus will have left. What I'm going to end up with at the tertiary position is a carbocation. And so while this is not, we're going to talk about a true carbocation where I form a carbocation and rearrange it, this ended up doing what's called the hydride shift. So we moved this H as if it was an H with a pair of electrons on it, where the hydrogen just kind of shifted over. It can only shift one position. That's another fundamental rule. So that, the molecule, okay, you're not going to let me form a primary carbocation. If I have enough energy, I can do this. And I can form a nice stable carbocation. Bless you. So it does that. The transition state for that's going to look like what? I'm going to have a partial bond to the hydrogen in a triangle. Oh, don't worry, we're going to do a ton of triangles in the next 7 days. But that's what the transition state would be. That hydrogen is partially bonded to both of those two carbons. So it shifts over. This carbon is slightly positive because it's becoming a carbocation, and the chlorine is becoming slightly negative. So that's what the transition state would look like, would be that triangle. Yes?
Does the hydrogen technically have two partial carbons at as well? Is that why it's
So the hydrogen is moving as a neutral atom, or well, it's moving as a neutral atom. What it's doing is it's taking a pair of electrons and shifting it over, but it never has a charge itself.
so it never changes charge?
No, it never changes charge. It starts out 0 here, it ends up 0 there. So it's not moving as an H minus, it's not moving as an H plus. The reason we call this a hydride shift, and maybe I should put that in quotes, is because basically the hydrogen is moving with a pair of electrons. Because the carbon that becomes the carbocation then loses its pair of electrons. And certainly the CH2 attached to the chlorine will never have a charge, because it would be a primary carbocation. So this can actually happen if you give it enough energy. Now, this can also happen with methyl groups, so that if I change this molecule and made it like this and reacted that with hydroxide, and I looked at all the products that are formed, I'm going to actually see a product that looks like this. And I can dissect this one a little bit better. Because what I could say here is, you say, but I have a primary with hydroxide, SN2. I'm going to say not so fast. Because this CH2 has a lot of steric hindrance around it. So when that hydroxide tries to do a backside attack, there may be not enough room for the chlorine or for the hydroxide to get in there and attack. And remember, that's what nucleophiles try and do first, is attack. They try and do substitution. If they're blocked from doing that, then the hydroxide can't react, so it just kind of hangs out. In the meantime, this molecule with enough energy would say, well, I can shift my methyl group and do exactly the same thing that I just did with the hydride. I can now shift my methyl group over and form a tertiary carbocation. And that tertiary carbocation can then react with the hydroxide. So the mechanism for this might look something like this. And I'm just going to, all three of these are CH3s. So this molecule says, I really want to react with that hydroxide, but it can't do SN2 because it can't do a backside attack. But if I have an SN1 mechanism, I can react with it. But I can't lose the chlorine, because if I lose the chlorine, I end up with a primary carbocation. So the methyl group then, it slides over, it does a 1-2, what's called methyl shift. And I should have said that the hydride shift was a 1-2 hydride shift. All the 1 and 2 means it's moving next door, relative numbering. And so if that happens, then I can kick off the chlorine so that I can now form a tertiary carbocation, and now that methyl group is now attached to what was the primary carbon. And the transition state for that would again be a triangle with the methyl groups, with the methyl group attached to both of the carbons simultaneously. The chlorine is going delta minus, and the carbon is going to become delta plus, because it's delta plus because it's going to be a carbocation. So if I did this reaction, I would get some of this product in my reaction mixture. And I would wonder where it came from. And then I would have to invent this whole mechanism, which nobody would believe to begin with. But then you would say, how else does it get over there? And then you would have to do some experiments and figure out, you know, what can shift and what can't. Yeah.
How do you know if it's going to be a methyl shift?
Because we're going to go to our first operating principle, which is that when you do a shift, when you do a carbocation, and these are also called carbocation rearrangements, which will be clear in the next example. The only way this shift occurs is to give a more stable carbocation. So you might say, but there's no carbocation to begin with. Right. Because if I lose the chlorine, I would get a primary. In this case, I'm forming a tertiary, which is more stable than the primary. So is this a valid shift? Yes. Because I'm forming a more stable carbocation. Is this an SN1 mechanism? It is now, because it formed a carbocation. So a hydride or a methyl group can shift to the next position if it forms a more stable carbocation. Everybody kind of with me so far?
So did you like update the chart in that if you have like a leaf nucleophile, then it would be also down with like
I'll give you, when I want you to do a shift in a mechanism, what I normally do is I give you the reactant and then I give you the shifted product, so that when you write the mechanism, you have to realize that a shift occurred along the way to write the correct mechanism. The only addition to our table, honestly, is that SN1 is now accompanied by E1. So this is an extreme example. And the only reason I'm showing you like this example, and maybe I'll show you the exact example that we did down at OU. But it's a second semester reaction, so let me try and put this. So what our goal was to do is we were going to take tertiary butyl chloride and we were going to react this with, I don't think we were using iron trichloride, we were using iron trichloride, not aluminum trichloride. Now what we're going to learn next semester is this, using iron or aluminum or silver will form a carbocation because those metals will grab the chlorine off the carbon. So in this case, what happens is the chloride would transfer over to the iron to make FeCl4 minus, because it picked up a Cl minus. And that's a great way to generate a tertiary carbocation. We were going to add that tertiary carbocation to a benzene ring to make a tertiary, add a tertiary group to the benzene ring, and then I think our goal was to figure out where the tertiary butyl group added. But we'll deal with that in organic 2. But we can generate a carbocation by reacting an alkyl halide with iron chloride is what I want you to imagine now.
So the carbocation and the iron chloride, they're like two separate things.
Right, they're two different ions.
So would you grade it as like plus in between?
Yes, they're just two ions. So here's what happened. When I went to the stock room, I accidentally grabbed this. I actually grabbed isobutyl chloride and not terse butyl chloride. And so about halfway through the experiment, a young scholar, because they're all young scholars down at OU, because academics are what's on most people's minds after partying. I think it's changed a little bit since I've been there, or maybe it hasn't, I don't know. They said, hey, we're using the wrong stuff. And I said, what do you mean? Well, we're using isobutyl chloride instead of terse butyl chloride. Does that mean we need to start over? And I said, no, you're going to get the same product. And then they looked at me incredulously and said, well, how are we going to get the same product? And I said, well, that's going to be your post-lab question, to write the mechanism of how you're going to get the same product. And they did. They did get the same product, and some of them wrote the mechanism, because we were talking about carbocations in lecture. And so you may say, well, what happened? What happened was, as the chlorine was being ripped off by the iron, the only way that was going to form a stable carbocation was to have the hydride shift over at the same time to then make the tertiary butyl carbocation, which then ended up adding into the benzene ring. So they got the same product by this hydride shift, which we had or were talking about it roughly at the same time. So I said, we'll write the mechanism of what happened with the isobutyl chloride so that it gave you a terse butyl carbocation to add to the benzene ring. So in this case, it didn't matter. So if there's one reaction I know that absolutely does a hydride shift, it's this one. And this is the more difficult of them because the shift occurs at the same time that you're losing the leaving group. So this is going to happen in a concerted mechanism, shift halogen leaving, which means this kind of mechanism is going to happen in a primary system where the halogen is attached to a primary carbon. Now you might say, where are we going to see carbocation rearrangements? Number one, you're going to see them whenever I tell you to see them. My biggest problem with, I'm not sure if if the same person that writes the book writes problems, but in many textbooks, the person that writes the study guide problems is a different person than writes the book. So the person who writes the study guide problems gets all happy about carbocation rearrangements, and they occur everywhere, when in reality they probably don't. And they don't give you any idea of when you should rearrange or not rearrange, which is why I take charge and just say, you're going to rearrange when I tell you to rearrange. As long as we follow the basic rule. Well, there's a couple basic rules. Number one, you're always going to form a more stable carbocation. Number two, you only get one shift. You can't just keep shifting. So you get one shift to a more stable carbocation. So here's a reaction where you might see a shift. And then what I will do is I'll leave this to you to maybe try and write the mechanism for tomorrow. I'm not assigning it yet, but could you write the mechanism to form that product from that reaction? So if I took the chlorine is on the ethyl group outside the ring, so that's we never did do complex IUPAC naming. That would be a 1-chloroethyl parentheses group. And then it would react to form a ethyl cyclohexanol. So if I gave you this kind of problem and said, write the mechanism of this, you're going to have to recognize that this does a hydride shift. So could you write the mechanism of this? And then for these reactions, you always form the carbocation first, and then you do the shift. The only time you're going to go the shift, eliminate the leaving group, is if it's a primary system. This is a secondary system. So you're going to form the carbocation first, then do the hydride shift, and then have the water attack. Okay. So I would like you to try and write the complete mechanism for this so we can start with this tomorrow. And then we'll talk a little bit more, but this is a valid shift because I'm going to go from a secondary carbocation to a tertiary carbocation. Okay. The reading assignment right now is online, and it is much larger than it will be when I go back and I edit out the stuff we haven't done. So, yeah, it is. So, okay, so we're actually talking about carbocation rearrangements, which starts in section 3.12, but there are no problems in 3.12 to do. This is talked about in 8.33. Then 9.1 has definitions. 9.2 has stability of alkenes. 9.3 has reactions of alkyl halides in E1 mechanisms. 9.3.1 has which reaction dominates. I think we've talked about that. SN1, if there's a nucleophile, it tends to dominate. E1 is kind of a side reaction. There is a section on 9.3.2 effective temperature. Section 9.4 SN1 E1 reactions, regiochemistry, which regiochemistry is just, do I form the one double bond or the other double bond? And selectivity of E1 products, which is Zaitsev's rule. Then 9.5 and on, we will talk about tomorrow for the rest of E1. And then we'll jump into E2. And then we'll be doing, so we're not going to get to alkynes unless I went hyperspeed. We're going to go through and react alkenes at the end of this week and then next week.
I didn't. So after reading your email about what was going to be on the exam, I did the